Thank you, Ravi. Like Ravi indicated, Dr. Yusuf Young couldn't travel to be able to present his work. As a former PhD student when I was at Penn State University, he started to work on this area of concrete interface. So I am very happy to present his work and see where he's taking this knowledge. So just to put us in the background, and maybe this is a wonderful continuation into the first presentation that we saw this morning of looking at bond between externally bonded systems and concrete. And what you see in here is that as we use these FRP systems for strength and rehabilitation, many times we are depending on the interface between the concrete, epoxy, and FRP to carry the work, to transfer the stresses to the form, to reach the level of strengthening that you as a designer or you as a researcher are expecting to see from that. So what Dr. Young has done is to go a little bit deeper into what do we really mean by the interface and how does that interface works. And the way he's doing it is to be able to try to characterize these failure mechanisms that you can see at the interface. So when you see this testing, for example, that our first presenters show of the single lab shear test, and you can see fracture between the bonded FRP and the concrete, really at what level are you seeing that failure and what is this happening? So what it has in here shown is that some of the terms that I'm going to be using today to describe failure, and it's really to look at when you have a crack, where is that crack going? Is a crack that is happening mostly on the concrete side? So if I were looking at this single lab shear specimen being tested to failure, would I be seeing only concrete being exposed? In that case, we will call that a cohesive failure in the concrete. But it might be that we are seeing some little areas where the epoxy is showing, in which case the crack has moved or has migrated into the epoxy side. So the properties of that epoxy are important. And in that case, you have what we call the cohesive failure of the epoxy, but most likely you're going to be seeing cracks that are in between that are in the concrete side and in the epoxy side, and they migrate back and forth. And those will be what we call the interfacial failures. And that is really the area where we are interested, because is the key to unlocking the understanding of this very important layer, and to be able to figure out what effects, whether they are environmental effects, temperature effects, sustained loading effects, might affect that, and how we can predict behavior, and we can maybe come out with some really good equation or design equations to be able to consider what is this happening, and what is that important to us, because all these structures that we're strengthening out there are going to be having these materials attached to them for the rest of their service life, and we're talking 75 years. Sometimes maybe we want to be able to achieve 100 years. So what does that really mean in the long term is part of what we're trying to look into. Two specimens that he was able to explore for this interfacial investigation was the single lab shear specimen, which you have seen descriptions of that, and also this 3-point bending specimen that was simulating the Rylam test that is done to be able to determine properties of concrete. But in this case, it was again saw, cut, and then glued back together with epoxy. So you could also have the information of how the crack is migrating as you're testing the specimen, and whether you're getting cohesive failures in the epoxy side, in the concrete side, or you're really having an interfacial failure. So what I'm showing in this presentation is not going to be focused on the experimental testing of all these specimens, although if you're interested, the paper has all the references where you can go and find that information. But what I really wanted to focus on is, what do we do with once you have failed a specimen? How can we get even more information from the tested specimens? And in this case, what he was using is image segmentation. And with that, he was able to kind of poke a little bit more into the fracture surface and see if we can identify some changes that were happening. And again, I hope that this is a useful presentation for all of you that are doing this wonderful testing and trying to get some data to see maybe you can use something like this as well, this additional tool to poke into your fracture surfaces and be able to find something in addition to that. Image segmentation has been used in many different fields. You have used it in medical field and the food industry, but in this case, what we're doing is trying to identify a image information that you have that you can take, that you can capture and see how that information key changes with respect to a certain variable. And what he was doing it is be able to take a look at these photographs of fracture surfaces and identify from these photographs percentages of epoxy, interface, interfacial failure, and concrete failure, and how those values change with the variables that he had in his specimen and his testing, and be able to see what happens from that. So a quick recap of the testing that he did. You have in here all the properties. 24 single lab shear specimens were tested, 30 3-point bending specimens. Material properties are indicated in here. I see they're all international units, since he's in South Korea, no longer at Penn State. But these are the typical standard specimens that he's got in there. For somebody's interest, I see a 7-inch bonded length of the FRP of the single lab shear specimen. The interesting thing for me is to talk a little bit about what did he do with that. So in addition to just making the specimens and eventually testing them to failure, at Penn State, when he was a PhD student, he was also looking into sustained loading. So with my colleague Chuck Bakis, we were able to devise a sustained loading setup that allows to be able to provide a controlled sustained loading both into the single lab shear specimens and into the 3-point bending specimens. And as you can see in here, we were playing with different variables. We looked at the curing time for the epoxy. We looked at prior to do sustained loading. We did a sustained loading for these specimens. For the shear lab specimen, the sustained load level was about 50% of what you were expected to be the failure. For the 3-point bending specimens, that was about 30% of the ultimate failure. We had some temperatures, again, that were subjected during the sustained loading regime and a period of time. So how long between a short term of sustained loading and a long term of sustained loading, and what happens with that. What I have in here is a photograph of the single lab shear test after all these different variables. You take the specimen now and you test it to failure. And I think Christian would probably enjoy to look at all the details of the testing. And yes, we did measure, we took pictures in several directions and used DIC as well to be able to capture if we were having out of plane deformations as well, and strain gauges to measure bond, the slip and bond performance and be able to derive information from that. From the 3-point bending test, it was again, like I mentioned, based on Ryland. And the idea after you take this test, which is really control under this is under crack opening controlled displacement, crack opening controlled testing, is to be able to capture the energy that is taken to drive this crack. And based on that energy, then you can have a measure of what you could use in your modeling as the cohesive crack energy that comes from this interface. And you can use that as one of the fundamental properties to model now your structure, because you have that information of how much energy does it take to drive a crack through this interface that goes between concrete and epoxy. So as you can see here, these are some of the results of what was obtained, the load CMOD, plus at the top, and then at the bottom what the fracture energy that is derived from this testing and what information that you can use in that case. So more interesting in here is now let's take a look at this idea of the sustained loading effect. So what happens if I measure the sustained load effects versus the duration. And from this testing for the single lab shear test, I can see that there is definitely a clear evidence that you have a decrease in that sustained load effect. So the changes in the ultimate load are decreasing as you keep increasing the sustained load in duration, and that is irrespective of what the temperature that you have during the curing time. In the case of the 3-point bending specimen, we have in here tested the total fracture energy in your vertical axis. And then you have in the horizontal axis, you have different things. You have 7-day cure specimens. You have a 90-day cure specimens. And in here you have the blocks for the different sustained load duration. And again, there is this pattern that shows that as you increase your sustained load duration, you are seeing also a decrease on your fracture energy, regardless of whether you did a 7-day cure or 90-day cure. Or in other ways, irrespective of what the curing regime is, you're gonna see this change. So for the presentation today is like, okay, we are observing that as a global behavior. That is what you will get from your laboratory testing. But what about inside of these crack areas? Is there anything else that we can get from this testing that will kind of help us better understand why we're seeing these patterns of decrease in fracture energy? So what we have in here is just the idea of how do you use this fracture surface image to be able to be processed and be able to use it to qualify and quantify the changes that we're observing. So on the right side, put it in here, what we're doing is we are detecting epoxy areas in the fracture surfaces. We're using image acquisition to be able to change the color of those epoxy areas into something that can be clearly identified and quantified. We are superimposing epoxy stains on both areas of a failure surface, and therefore we can identify interfacial failure and cohesive failure in the epoxy. And then we just do 1 minus that, because if it's not interfacial failure, if it's no failure in the epoxy, what is the only failure left? Failure in the concrete. So by being able to very clearly and clean identify those 3 possible failures, now we have something that can be digitized and translated into percentage of areas and modified into all the different specimens. So this was kind of like a nice trick to be able to take information to quantify it. And I think that's part of what I see the researchers sometimes needing is, okay, you have this beautiful data. Is there a way to go a little bit more in depth and be able to poke this data and get a little bit more information on that? So how do you do that? And I think in this slide, Dr. Young is showing how you can use this image processing segmentation. And I think the key is to identify for the mechanism that you're trying to predict or the variable that you're trying to measure, what is the best type of space that will allow you to measure these changes. So you can go into the RGB space, which is basically you go with the red, greens, or blues, and with that change, you can also go into a space where it's measuring intensity of colors. There is what they're calling here the YCRCB space where you can look into different variables of the different colors and see again which one of these spaces of color information is sensitive enough to capture the variations of the variable that I'm interested in. He ended up using this, which is called the CIE lab color space, and then in this one he can quantify really minor changes in color. And with this very minute changes in color, he can use that to be able to do a sensitivity analysis. So here's a photograph of a typical failure that you will probably see. This is a 3-point bending test. So notice the little small areas in blue. That's the epoxy that is peeking through. And then you have concrete. Then we use this CIE lab image segmentation to be able to identify all these small areas of blue and all the variations of blue, and then we can identify those to be as areas where there is epoxy. With that information, then we start the step one of being able to look at this fracture surface, identify these areas with epoxy, and start the process of looking into what do we do with that information. So in the 3-point bending test, when you go and look at the two fracture surface, you're going to have two sides, and those two sides are going to have areas with epoxy. And again, they might overlap or they might not overlap. But that information is telling us the crack that was going through these surfaces, whether it was going through epoxy on both sides or concrete on one side and epoxy on the other side. Same thing with your single lab shear test. When you look at the surface on the concrete block and on the FRP, you are looking at a combination of areas where you might have epoxy. And this is what, as an image, is being processed to be able to dig into this information. So, for example, here it is two pre-processed images. Here is the same two images where the locations of the epoxy have been identified. And now what the next analysis does is that it takes these epoxy areas and it assigns a very distinct color within this image processing space that allows you to do combinations. So for one of the faces, it assigns the epoxy stains with a green color, and the other side of the fracture space assigns those epoxy stains with a red color. And then by being able to do this really clear difference in coloration in these areas, then you can have an algorithm that can very quickly analyze what is happening to these two surfaces and combine them. So if you have green on one side, green epoxy and red epoxy, and you superimpose the two images, then you can say that when you have those two images combined, you're going to have probably a clear case of epoxy failure or crack going through the epoxy. We're going to call that concrete cohesive failure in the epoxy. We're going to assign it a new color. This is going to be the yellow color. But if you are in a location where you might have concrete on one side and epoxy on the other, then now it's going to be a very clear interfacial failure. And I don't want you to get too lost on all the colors, but the nice thing about being able to have an algorithm that talks to the image and be able to fix the information is that it can tell you areas, it can tell you changes in the areas, it can also show you maybe even a sequence of how the crack was propagating. And it's all that coming from the photographs of the fracture failure that you typically just take a picture and then put it in the trash can after you're done. So here's the last step, which is once you have the superimposed failure side, then you can identify which ones are cohesive failures in the epoxy. You can superimpose those two images and get that information in locations in areas, and you can assume what this is not a good. You can also look at the interfacial failure, which is the ones that are identified as yellow, which you can all see here with your eye. And then, again, an algorithm of comparison, correlating things, adding areas, subtracting one area over another, and be able to measure what is the area that is covered by interfacial failure, what is the area that is covered by concrete epoxy failure, what is the area covered by none of the above, and that will be your cohesive failure in the concrete. So one more photograph in here. I think this is a summary of just everything that he was showing of the different steps. Let's move into the results, because I think that will be probably an interesting thing. So this is the same data that I showed you earlier for the 3-point bending. And then what we are superimposing in there is be able to capture what happened with the interfacial failure. So look at now at the vertical axis, and look now how we are plotting the sustained loading effect, the fracture energy, but now we're looking at what happened with the interfacial failure area. So for all these specimens, analyzing the fracture surfaces and identifying how much area of the fracture surface corresponds to interfacial failure, then we can see a very nice correlation that shows that indeed, as you were seeing that global behavioral changes in fracture energy, it corresponded to a decrease in your interfacial failure surfaces. And in here we have, for sustained loading, interfacial failure as a percentage, fracture energy in here, and we can also see in here this trend. So his conclusion again is that you have this reduction of fracture energy, and it can be correlated with an increase in the interfacial failure mode as you are going with different sustained loading. These are the conclusions from his testing, and I'm just going to read them in here. The duration of sustained loading period adversely impacts the bond strength and the overall fracture energy in the specimens that were tested. The image segmentation approach described in the study was effective for evaluating the performance of the concrete epoxy interface in 3-point bending specimens, where the epoxy, the FRP, and the concrete substrate are distinguishable by color. I think what I need to say in here is, if you notice the information from the single lab shear test was not as clear. And that's because, unfortunately, this was CFRP, which is black, and the epoxy that was used from the manufacturer was blue. So as you put blue on black, then the difference and the hues that you're trying to capture are going to be less significant as when you do blue on concrete, which is going to be on the whitish, grayish range of the spectrum. So, lesson to be learned: if you want to capture what happens between the FRP and the epoxy, you need to make sure that those two colors are as different as possible to start with. And then his last conclusion, that an accurate evaluation of the failure modes is going to be able to help you improve the way, not only maybe quality check, how do you do your testing, but also when you're doing your testing to be able to come up with the basic equation that is going to go into your design, how much of that really is being affected by these different variables that we're studying. And I think with this, I finish my presentation, and I'm happy to take any questions.